So the basic unit that we will describe is this. It's a tensegrity prism. It's made of 3 bars. This we will 3D print, and cables. In the 3D printed examples, the cables of the 2 bases have been replaced by plates. Okay, but you can have cables, and then 3 cross cables, 3 cross bars. This structure has a particular response under compression. So if you have this system and you compress it, what happens is that the 2 bases twist with respect to each other, and then you change also the height, and contemporarily you twist the 2 bases. Okay? You compress, you reduce the height, and contemporarily the 2 bases will rotate with respect to each other about the vertical axis. And this is what you will get. So phi is the angle that of rotation of the top base with respect to the bottom base. Okay. So it's the angle at which the top base is rotated with respect to the. If the phi is 0, the 2 bases are basically parallel to each other. If phi is different from 0, you can twist in 2 directions, and you will have the 2 bases that are twisted with respect to each other. And you will have a series of admissible configuration. So this is phi equal to minus pi over 3, so you rotate this way. And this is the limit. This is a limit because at this value of phi, the strings, the cross strings touch each other. And that we cannot get lower than this value. Then if we go to phi greater than 0, we can go up to pi, the value at which the bars touch each other. And we will see this is a noticeable value of phi. So we will see this is a noticeable value of phi over 5/6 of pi, because when phi is equal to 5/6 of pi, this value, the system becomes pre-stressable, so can be freestanding. Okay? Those are possible configurations geometrically, but in order for those configurations to be reachable, you must apply forces. If you want a shape that is reachable without applying forces, you have to choose this one. The other one are reachable between this range, but applying forces, external forces. This one is gives rise to a freestanding configuration. Freestanding is the one problem with the tensegrity is to find the freestanding configuration. So the configuration that is in self-equilibrium without external forces. Okay? So this basically is the configuration that you obtain when you try to mount the system. If you try to mount the system, there is the final string. You start connecting the pieces. The final string will give you this freestanding. You have to stretch the final string until you get the structure in freestanding. The last tensioning will give you this freestanding. This is the configuration that you can achieve when you mount the structure. The other configurations are not achievable because require external force. If you want to mount the structure, there are just few configurations that you can get, and those are the configuration in which the system is in equilibrium without external forces. It's a freestanding configuration. Okay? So the search for freestanding configuration is a particular branch of tensegrity research, which is called shape finding. In tensor prism, there is the freestanding configuration is the one at which the two bases are rotated over an angle equal to 5/6 of pi. So we solved the equilibrium equations of the system, and we found the solution for which there are forces without in the members. Those are x1, x2, x3 in the cross strings, the forces in the base strings, and in the bars, by solving the equilibrium equation of the generic node, because under vertical loading, you can the equilibrium equations of each node are all equal to each other. So it's important that you examine the equilibrium equation of one arbitrary node. There are three forces. The forces in the two base strings, one one bar and one cross string. This one will be the cross string, the bar, and two base strings. Let's call x1 the forces in the diagonal strings, x2 the forces in the base strings, and x3 the forces in the bars. By solving the equilibrium equations, you obtain a formula for x1, x2, x3 as a function of the phi of f. F is the external load applied, assuming that there is an external load, F, vertical. You obtain a formula for the forces. The self-standing, the freestanding or self-standing configuration is the solution in which you have x1, x2, x3 not 0, with F being 0. If you can have x1, x2, x3 different from 0, when F is equal to 0, that gives you a pre-stressable configuration, so a configuration in which the structure is in equilibrium under self-equilibrated forces. There are tension and compression that are self-equilibrated, do not correspond to external load. That's the mounting configuration or the freestanding configuration. Because when you make a sample and then you put on the table, just discarding the weight, and it has to be freestanding. It will be freestanding if you have reached the configuration in which this is possible. So we analytically found that there are actually two configurations in which the bars and cables are in equilibrium without forces. There are two, but only one is this other one is this one. In this one, the strings go slack, would be compressed, which is not possible. Only one is really a tensegrity configuration, which is this one that I have shown before. Okay, so now we considered the response of this unit starting from this configuration up to this one, compressing, starting from the freestanding up to the totally compressed configuration in which the strings, the bars touch each other. Okay, we want to study the response. Now, having detected this is the freestanding configuration, we study the response of this unit under compressive forces, now non-zero, starting from the value of 0 in the freestanding and then compressing and seeing what happens. And we found an interesting result, that this, if you study now the compression from the freestanding configuration up to the locking configuration, we call this locking configuration because the bar touch each other, so that you cannot compress anymore, or if you compress, the scheme is changed, the structural scheme is changed. We solved this equilibrium problem for compression from the freestanding configuration, and we found an interesting result. These are the details of the equilibrium problem, because just give you the global sketch. How do you solve this equilibrium problem? Now, you start from the configuration in which the forces are in equilibrium without F. Now you apply an F. The geometry of the system is ruled by three kinematic variables, which are the twisting angle, the length of the base strings, the side, the edge of the triangles. So the twisting angle is shown here, is one variable. Another variable is the length of the edges, of the base edges. Another variable is the length of the cross strings. There is also you can take, this is one variable. There is the twisting angle. You can take as a third variable, you can take either the length of those strings, or the length of the bars, or the height of the prism. They are all related. The third variable will be either the height of the prism. Those are the relations giving the length of the bar and the length of the strings as a function of L, phi, and h. So if you have L, phi, and h, those three variables describe the kinematics of the structure. Okay? And the B and S will be dependent variables. Okay? Because if you compute the length of these two bars, the length of this member will be a function of L, phi, and h. Okay? So it's not an independent variable. Only three are the independent variables. To describe the kinematics, I have the twisting angle, the